Hello, this video is entitled Lagrange Multipliers. Now, Lagrange multipliers are a technique to find the optimal values, minimum or maximum, of a function with a given constraint using a little bit different technique than the second partials test and that kind of stuff. But also this works for one or more constraints, so more constraints would not work for the second partials test. But just real quickly, I'll give you an intro here. It doesn't matter if you don't understand the geometry behind it. That's okay. We'll get right to the technique of how to apply it. But just real quickly, I'm just going to show you this picture, and then I've got a graph of another one later I'll show you too. Well, if your function, which is f, is going to be subject to this constraint g, where g of xy will equal some value c, and then f of xy will just be some function with x's and y's. But it has to be subjected to this. It has to be true here. So on this graph, this ellipse, and this particular one, is the constraint equation. And what these level curves represent, they represent the function f of xy if you set it equal to different values. They're using k here, and sketch the graph. Well, the optimal point is going to occur at the point of tangency, where those two graphs hit each other. Now, there's a rule whenever you have two graphs tangent like this, and that's what's going to lead us to, it's going to generate another equation for us to help solve the optimal value, is that two curves tangent at a point if and only if their gradient vectors are parallel. And this means that also one of them will be a multiple of the other. They may not be the exact same value for the level curve, but they'll be parallel. And remember, of course, parallel vectors are a multiple of each other, so we've already learned that. And the gradient's what produces the normal vector, which we've already seen in a previous section. So what we're saying here is we now have this extra equation here that says the gradient of f will equal this scalar value called lambda times the g. And like I said, that gives us an extra equation to help us solve for what the values we need for x and y. And we'll see the method here in a minute. So there's the theorem, Lagrange theorem, that says there exists a real number lambda such that the gradient of f at that x0, y0 point will equal lambda, a multiple of g x0, y0. Now, we're not specifically worried about what the value of lambda is. Sometimes we may solve it in a problem, sometimes we won't. It just depends on how you solve the equations. We don't really need lambda. I was reading there were some applications, I believe, in both physics and economics where the value of lambda actually does tell you something. But here we're trying to find the value of specifically the x and y that would generate our optimal solution, max or min. Okay. Now we'll see this can expand to more variables. So let's see, we say we have a max or min subject to this constraint, g of xy equals c, and then we simultaneously solve this system of equations. So the gradient of f of xy equaling the lambda of gradient of gxy. So the gradient of fxy is just fx fy, like the subscripts, the partial derivatives, and then g will be gx and gy, and then the lambda appears right here. So that's the same thing as saying the fx partial equals the lambda of gx partial, the fy partial equals the lambda of the gy partial, and then your constraint. So in this particular equation, system of equations, we have three equations and three unknowns. With, like I said earlier, they're really the only unknowns we specifically need are the x and the y. If we happen to solve for lambda, that's fine, but we don't need it. And then if you obtain more than one possible set of values from this, then you would just plug those different points into the original function. And if you're looking for a minimum, it would then be the smallest. If you're looking for a maximum, it will be the largest. If you work this out and you only obtain, one optimal value, then you pretty much can assume it will be either a minimum or maximum based on whatever the question was asking you to find. It's when you get more than one of these that you have to sort of test it to see which one's the min, if that's what it's asking for, or which one's the max. But if you only get one, that's pretty much going to be the answer. So I basically have those rules in just sort of written out like this. And this can expand also if you have a function of x, y, and z. It's still the same basic equation where the gradient of f equals lambda gradient g. And you see, so you have these three equations, and then the constraint makes four equations. So this time, now that we have variable z, we have four equations and four unknowns. Yeah, it's very important that we need to have the same number of equations and unknowns. Now this example was given in a previous video, the section before this one. I should have labeled it in case I'm using a different textbook. This may be irrelevant in the future, but anyway, this section would be a section that follows finding the extrema of two functions. I believe it's called applications of extrema. So it's using the second partials test to find mins and maxes. So I'm taking a problem from that section, and then now we're applying Lagrange multipliers to it. In fact, I think I will bring that problem up just to show you. So here is that problem from the previous section. Now I'll go back to our notes a little bit, just kind of give you a feel, for the kind of the work involved there. And there we go. But now let's go back to see how it's handled by using the Lagrange multiplier technique. So we're trying to find three positive numbers such sum is 32. So that's going to be your constraint where x plus y plus z equals 32. So in other words, g of x, y of z equals 32. And here's the function that we're trying to optimize here. In this case, it's maximum. So we're looking for a maximum value. So it's x, y squared, z. It's written right here. So let's get the Lagrange equations right here. So get everything written out here. So the x partial of xy squared z would just be y squared z, and then the g partial. In fact, this is just coincidence for this problem, so I'll go ahead and just mention it now. But all three partials for this g constraint are going to be a value of 1. 1x, 1y, 1z. That's just a coincidence for this problem. So these are all going to happen to be lambda times 1. I didn't just repeat the same thing 3 times on purpose. So let's look at the constraint of a partial for y for this part here. So the derivative would be 2y, so it makes it 2xyz. And then the last one, the derivative of z would be 1, so it's xy squared z. So we have these three equations. And then your constraint equation is always one of your equations. So the constraint always counts. So we have 4 variables, 4 unknowns. Now, once you get this set up, there is not a specific definition or process or rule how to proceed from here. It's strictly just algebraic technique. So, the rules are clearly defined on how we get this system of equations right here. But how you proceed is up to you. Because oftentimes, when I teach this in a face-to-face class, I'll work some problem out and the student will come to me and say, well, hey, I went with this method and got the same answer, and, is that okay? And if it's done correctly, of course, but if it's done correctly, absolutely. So the way I go about this is not the only way it can be done. But we're all working from this set of 4 equations. So what I did, I said here, combining 1 and 2. What I mean by that is that I'm taking equations 1 and 2, and if we say that we have y squared z equals lambda and 2xyz equals lambda, you can then say that lambda equals lambda, in other words. So I can set those two equal to each other, and that's what I did. So I set them equal to each other, and one thing I'll mention, mathematically speaking, is you don't want to. It's not a good idea to divide variables when you're solving equations. That's something you shouldn't do, because you lose solutions where they equal 0. But that's okay in this case because it says 3 positive numbers. So if we eliminate solutions that have 0 in them, that's all right. But keep that in mind if that wasn't the case. And let's say we were finding critical points to use a second partials test. In other words, we weren't trying to optimize anything. We wanted all critical points until we did the second partials test. You would not want to divide by variables because you wouldn't want to lose 0 solutions. But here, it's okay. So I divided by yz on both sides as the common, which I could have brought the right side over to the left and factored out a yz either way. But long story short, these first 2 equations lead to the fact that y will for sure equal 2 times x. Okay. Now I chose to combine 1 and 3, as long as it's 2 different ones. I could have done 2 and 3 if I wanted to, and that would have been fine. But you're basically combining any 2 of these 3. You won't need to do all 3 of them. Well, so I take the first one and the third one, because now this one also equals lambda. So you set them equal to each other. I divided both sides by y squared. So now I know that z equals x. So at this point, you're trying to get, essentially a single variable in terms, you're looking for the common variable and you're solving for it. Now, what I normally probably would have done in this thing is I would have said that x equals y over 2 and x equals z. No, I'm sorry, I got that backwards. You saw, okay, y equals 2x and z equals x. That's what we're looking for here. Because ultimately, we're just trying to get this down to one variable. So you can then you go to the constraint equation. X plus y plus z equals 32, and once you get this down to one equation, so this is the variable you're solving for down here, whichever is the common variable. So we know that x equals just x. So y is now known as 2x, and then z is x. So you have x plus 2x plus x equals 32, which means 4x equals 32. And that leads me to x equals 8. And then we know that y equals 2x from right here. So it'll be 2 times 8, which is 16. And then z equals x, which equals 8. Slide over to this other one. Now, so that's the same answer we got over here, but it's a lot less messier. Now I use the Extrema command in the Maple software, and it got the right answer. This time I use the Lagrange multipliers. The only difference here is Extrema would work, obviously, because it already has, but I just did this for the heck of it, just to show you. The Lagrange multipliers is also going to show you the value for lambda. Now, the Lagrange multipliers is going to give you what's called every possible feasible solution to the scenario, meaning anything that would possibly work. but it doesn't mean every one of them is the best answer. Only one of them will be the best answer. This first one's kind of weird, but let's look at the second one. It's picking ones that satisfy the constraint. I'm not sure exactly what method it is to extracting those, but in other words, 0, 32, and 0 would satisfy the constraint. It would make it true, but clearly it's not going to be a maximum because it's going to produce 0 here. So I'm not sure how it's coming up with those other ones, but anyway, here's our answer: 8, 16, and 8, and the lambda is 2048, which we didn't really need. We could have found out if we want to. And there's just the actual optimal value when you plug it back into this equation. So xy squared z be 16,384. All right. That one had 3 variables. Now we're down to 2 variables. So we're trying to minimize this function 3x plus y plus 10 with the constraint x squared y equals 6. So we have to get our Lagrange equations first and foremost. So here they are right here, the general form of them. And then now let's get what they actually are based on this particular problem. So the constraint equation, which is f, that's the left side. So the x partial will be 3. And then the constraint for the g right here on the right side, with respect to the first partial with respect to x, will be 2xy, and there's the lambda. And then for the next one, fy, the y partial here would be 1. Here's lambda. This constraint, x squared y equals 6. With respect to y would just be x squared, so you have lambda equals x squared. And then here's the constraint equation. So we have 3 equations here and 3 variables. So once again, I solved for lambda equals, and lambda equals, which, you know, is a very common technique to solve it. Now, when I get a little more sophisticated, it may not work that easily, but that's probably a good place to look. So because when you set lambda equals lambda, then you can set the 2 equations equal to each other, like so. So let's come down here. And so I set these equal to each other. I have 3 over 2xy equals 1 over x squared. And I cross multiplied 3x squared equals 2xy. And then once again, I don't care about, say positive here. Yes, x and y are positive. So I can divide variables. That is okay in this case. And divide by 2x. So you end up with y equals 3/2 x. And then it works out pretty well from there. So you just put 3/2 x in here for y. So you have x squared times 3/2 x equals 6. So if you multiply both sides by 2/3, you get rid of the 3/2. You have x cubed equals 4. Therefore, x equals the cube root of 4. Okay, no one said that these answers had to be integers or pretty numbers. It just said they had to be positive. So you get x equals cube root of 4, and we know that y equals 3/2 x, so y would equal 3/2 cube root of 4. So there's your xy point that would satisfy the constraint and give you, well, the minimum, I believe we're looking for here, right? Minimize. And let's see. So it's kind of a weird minimum value. I'll sort of say it verbally, but it's just, it's 3x plus y plus 10 is your function. So it'd be 3 cube root of 4 plus 3/2 cube root of 4. So actually the value is 4.5 cube root of 4 plus 10, which is around this decimal number I got right here. It's somewhere around, oh, they're coming up with it exactly, but yeah. Of course, they simplified they played around with that root. Yeah, just to tell you, the cube root of 4 is the same thing as 2 to the 2/3 because 4 is 2 squared. But that doesn't really accomplish anything, so I don't know why they did it. It's somewhere around this 17.15. So I'm just go back just to show you. I want to pick a couple of easier numbers. something that would satisfy, let's say, I don't know. Well, I could pick something really easy. Let x equals 1 and y equals 6. That would satisfy this constraint, wouldn't it? 1 squared times 6 would equal 6. But if I put that in here and have 3 times 1 is 1, plus 6, 3 times 1 is 3, excuse me, plus 6 is 9, plus 10 is 19. So you get a value of 19. 19 is not less than this 17.15. So you could sit there all day trying numbers that satisfy that constraint, and you will not get a minimum value smaller than this ugly answer here. So the ugly answer, or maybe I shouldn't say it's ugly because it's correct. So nothing correct should be considered ugly. All right. The Maple output, did give the correct optimal value here. As I was saying before, it reduced or changed the radical here, but this is the correct answer. These three values. Well, I'm sorry, two values, x and y. Then it's telling you what lambda is, which who cares? Then it's telling you the optimal. I just cut this off right here to not show any more of the wrong answers, so that's why that would have continued. Now I was playing around with Maple and just did this little thing here, but not important that you. But the purple, or whatever color that is the constraint graph here. X squared y equals 6. That's what's going on here. And those planes are the equation we're trying to optimize. 3x plus y plus 10 equals some value where I'm essentially creating level curves. Of course, in this case, it's not curves, level planes. And as that first picture was showing that I copied from that book at the beginning of the notes. Well, this isn't critical, but anyway, so I just kind of drew some of them. And here's the one where it actually intersects. So obviously, that's where they'll have the same normal curves coming out of them, normal vectors coming out of there. So if they have the same normal vector, that's what leads to the lambda. And this green line where this point hits on the xy plane, that's the values, that's the correct answer here. So unfortunately, these are kind of ugly values for this problem, but where that's hitting on the x-axis right over here, 1 point something, well, that's okay because the cube root of 4 is 1 point something. And then over here, it's hitting at 2 point something, which 3/2 times the cube root of 4 is 2 point something. So that's the value where this plane is hitting the curve. And like I said, on some of them, they'll hit at more than one spot. So if they intersected, which, I'm not saying you're even going to see the graph, but if they did, in theory, if there's more than one possible answer, you just test to see which answer is correct. I have an application example coming up here in this section where we'll have to do that. A lot of times these problems, it just ends up giving you one answer, and that's going to be the optimal answer. So it's already going to work. But I just wanted to mention that. Now here's another problem that was done in the section on applications of Extrema. And we're going to now apply Lagrange multipliers. Let's see. Positive numbers, so you can eliminate anything that's 0 or negative. So the product of the three numbers is 36, so x, y, z equals 36. And then we're trying to minimize this function, x plus 2y plus 3z. And I'm just labeling right here that your x, y, z, that's your gx of y, z, when we're coming up with these Lagrange equations. So the f partials, the fx, fy, fz are always the left side. So these partials will be 1, 2, and 3, pretty straightforward. Now the right side is going to be lambda times of x, y, z. The x partial will be yz. The y partial will be xz. and then the z partial will be xy. So I kind of went with a, lambda equal approach. And since we're back to, this is similar to a couple of problems earlier ago, that when you have three of these, the idea will be setting any two of them equal to each other. So this time I went with 1 and 2, and then 2 and 3. So like I said, you can pick any two pairs here. So I'm going to set 1 over yz equal to 2 over xz right here. Cross multiply. Divide by 0, as I'm mentioning there, we don't use the z equals 0. And you get 2y equals x. So there's one substitution we'll use. You take 2 and 3, these bottom two, you have 2 over xz equals 3 over xy. Cross multiply, 2xy equals 3xz. Divide by x gives me 2y equals 3z, so z equals 2/3 y. So now I have, so the fact that this is the common variable y, that actually means that's one we're going to be solving for, because we're going to replace the other two variables. In other words, we have x in terms of y, and you have z in terms of y, and then of course y will be y. So that's whichever one appears twice when you pick these two equations. It doesn't matter. It does not matter which one of the three it is. It's the common one is the one that we'll be solving for when we substitute in here. So x is 2y, y is y, and then z is 2/3 y. So you multiply this together, you get 4/3 y cubed. So I'll multiply both sides by 3/4. And that gives me y cubed equals 27. So y equals 3. And then if x equals 2y, so x will equal 6. And then z equals 2/3 y, so z will be 2/3 times 3, which gives me 2. So the optimal solution for x, y, and z would be 6, 3, and 2. So there's no way you can find any set of numbers that multiply together to be 36, that if you plug them into this equation right here, you'll get a smaller value than what we just got by using 6, 3, and 2, which, let's just, for example, what would it be if it was 6, 3, and 2? 6 plus 2 times 3 is 6, plus 3 times 2 is 6, so 18. So 18 is the value, function value, that's the smallest we would get with x, y, and z multiplied together to equal 36. All right, I paused for a moment to bring back up the 13.9 notes. I didn't put the Lagrange multiplier maple into that for that problem. I was going to if I didn't already had done this. So I just want to switch over to show you. See, it's telling you 18 is that value, the Extrema value, and then it's showing you that it's 6, 3, and 2 here. So the Lagrange multiplier command in maple would have done the same thing, except it would have given you the values for the lambda. All right, let's take a look at this optimization problem, where our goal here is to find the maximum possible volume of a rectangular box inscribed in the ellipsoid, x squared plus 3y squared plus 4z squared equals 12. Not that we would have to draw the picture for this, but I did create a graph here. So we're trying to find what points on that ellipse, if you then construct a rectangular box from it, would it have the largest possible volume? Now, what I'm going to do is instead of worrying about identifying all the coordinates, which we don't need, I'm going to treat this as a first octant problem and find where x, y, and z are positive, even though there technically are 8 vertices. All we need is the 3 values of x, the positive values of x, and that will be good enough. And then I'll do is I'll multiply this by 8, because when you find the first octant, that gives you, you break this down it's above the XY plane, below the XY plane, that would give you half and half of it. And then you break it around the 4 sections, quadrants along the XY plane. That would give you 4 above the XY plane, 4 below. So there's 8 sections, 8 equal sections. So you just multiply this by 8, and it's going to be x times y times z will be the volume of the one region. And then 8 would give you the volume of the entire thing. That way, it prevents you from having to find all the positive and negative vertices. So so there's your equation you're trying to optimize. Here's the constraint. So the Vx partial would be 8yz, because x would be 1, derivative. Vy would be 8xz. Vz would be lambda, 8xy, I'm on the wrong side. Derivative of z is 1. Now the right side, here's the constraint equation. So these partials with respect to x, y, and z would be 2x, 6y, 8z. And then of course the constraint equation. Of course they all have lambda. So we have 4 variables, 4 equations. And there's me just kind of saying the 8 equal sections and writing, kind of rotated around there a little bit to get a different view. So I set all 3 of these equal to lambda, and sort of similar to what you see me do in other problems. This time I chose to do 1 and 3, 1 and 2, and 1 and 3. There was another one where I did 1 and 2 and 2 and 3. That's fine. Like I said near the very beginning of this, is once you get your Lagrangian equation set up, there's not one exact way to solve for it. It's by whatever valid algebra techniques that you can use. So let's see what we have here. So we have with 1 and 2, these two equal each other. So right off the bat, I didn't show it, but I divided off the 4 and the z, because I know they could divide away. Then I cross multiplied. I get x squared equals 3y squared. And then I'll come down to do 1 and 3 and set those equal to each other. And this time the y's can be divided out. I get x squared equals 4z squared. Now, since the common one is the one that we'd be solving for, so that means that's why I had to do this right over here to the right. It's because I need to solve it in terms of x squared. So y squared then would equal 1/3 x squared, and then z squared would be 1/4 x squared, right there, to substitute. So here's our constraint equation. So I'm going to substitute the y squared, which is now 1/3 x squared, and the z squared, which is 1/4 x squared. 3x squared equals 12. And then x squared equals 4 plus and minus 2, but we're not using the negative 2, so we only need the positive 2 here. Because like I said at the beginning of the problem, we're just looking for the positive values. So now that we have x equals 2, we can easily find y and z. All right, so we got a little radical value for this one. 2 divided by root 3, because y squared equals 4/3. And this one you have z squared equals 1, because remember we're plugging in the 4 for the x squared. I could have written 2 squared, but so it's 1/3 times 4 for y squared, and then 1/4 times 4 for z squared. So z would equal 1. So that means the actual maximum volume then would be 8 times x times y times z. So x is 2, 2 over root 3, 1, and it's 32 divided by the square root of 3. That would be the maximum volume of the rectangular solid that you can inscribe in that ellipse. Now, of course, Maple is giving all kinds of answers here. Now, I can't figure out in these Lagrange multipliers, I think I mentioned that in another problem coming up, is I don't know how to restrict it to only show positives or anything like that. But well, let's see what we do have. Yeah, here's the one where they're all positive, though. Okay, so, and of course they just rationalize the denominator here, which I don't expect you to have to do. Oh, it looks like I left out the command to make it show what the lambda is. I believe, let's see if that was a separate command. Let me look back up here and see what was making that. Ah, yeah, I left out this thing that says output equals detailed. That's what brings out. It also brings out the maximum value. But you know, you got to figure if we got these numbers right, the maximum. Okay, so maybe I should have left that in there. But well, of course, Maple would have shown this as 32 root 3 divided by 3. But yeah, so that output equals detail would have shown the lambda and the optimum value of the volume. All right, this is kind of weird here. This is all the commands that I had to use to plot that ellipse and that paraboloid in there. I'm sorry, the rectangular solid inside that ellipse. Unless there was a better way to do it, I could not figure this out. But what I did is I literally plotted all the points. You know, all you got to do is just change the coordinates, each one of them, to the negatives in there, and all the possible, you know, combinations of positive and negative, and made it plot those points, and then made it draw a line segment between all those points. So that's how I built that rectangular solid. It was literally, I probably got halfway through this and go, why am I doing this? But actually the tricky part was just making sure that, you know, you got each possible combination here, you know, with all these negatives and positives. And needless to say, I would not worry about too much about that, just in case you were curious. Let's see what this example says. Minimize the total surface area of an open box with volume of 256 cubic meters. And find the minimum surface area. So essentially we're trying to use the minimum amount of material, whatever this could be, cardboard, aluminum, steel, whatever. We're trying to use the least amount of it to build a box that guarantees that we have 256 cubic meters in that box. So here's the function we're trying to minimize. Open box, that's the key. So I kind of just drew an x, y, z. But technically the way I drew that x, y, z is not critical. But, you know, as long as your equation is correct based on how this is labeled, that's the key. But based on the way that I labeled it with x, y, and going up with the z, you see that there's no top. So there's going to be an xy base, so there's only one of those. But then each sides will be two pairs of the sides. So I'm going to have an xz on this side and then one over there, so it makes two xz's. Then on this side, I've got a yz here and a yz there, makes two yz. All right. Now, and then here's our constraint. The volume, which is not affected by the open top, would be x times y times z equals 256. That's our constraint. Let's see what we have here. So I'm going to take the partials of this left side. So respect to x would be 2z, and that'd be 2y. No, excuse me, 2z, there's no x here, so that's 0, and then y comes from this derivative. All right. The next one, this is only the first two terms have z's, so the partial will be 2x plus 2y. Oh, I jumped ahead of myself to z, excuse me. But anyway, I'm pointing at it now. And then the y, only the second two terms have a y. So it'd be 2z plus x. Here are my lambdas, and now the constraints here, the partials here would be yz, xz, xy. And of course, x times y times z equals 256. So I went with a lambda equals lambda deal. I did not show the step of solving each of these for lambdas, but that's what these are right here. So here's this first lambda, so it's 1 and 2. And the second lambda would be 2z plus x over xz. Then we have cross multiply, and we don't want anything with 0 in it. So actually these x, y, z's would subtract out and cancel. And then when they cancel, I divide it by what common 2z squared on both sides. So all that basically reduced down to x equals y. So it looked kind of ugly and scary, but it turned out to be beautiful. X equals y. So now I have 1 and 3. Same idea. So here's lambda equals lambda. Cross multiply. This one we have matching 2x, y, z's. They would subtract off and cancel. I divide both sides by y squared. That leaves me x here and 2z there, so x equals 2z. So you can see that since x is the common variable, that's the one we have to solve for and plug in. So that means I have to go one more step here and then let z equals 1/2 x. So now I can say y equals x and z equals 1/2 x, and then we can solve for x. So now I'm using the constraint equation of x, y, z equals 256. So x is, of course, just x, y is x, and z is 1/2 x. Equals 256. Multiply both sides by 2. That will give you x cubed equals 512. So this worked out nice. Obviously we didn't have to get an integer. It could have been a cube root of a number. And x equals 8. And y equals x, so it equals 8. And then z equals half of that, which is 4. So 8 by 8 by 4 for this box. So an 8 by 8 base and a height of 4 will satisfy the volume of 256, and it gives you the smallest possible surface area that can be found. And then here's what that surface area is by plugging the numbers into here. So these are the values that give you the smallest surface area. Here's the actual surface area, 192 square meters. Now, as I mentioned, I believe at the beginning of the video, this technique, unlike using the second partials, here's where we really need the Lagrange multipliers, even though the Lagrange technique is a lot of times way more convenient. But here's when you have two constraints. So we have to find, optimize a function then that satisfies two different constraints. Now here's what happens to the Lagrange equation this time. So this we had, before g was the constraint, and g still is a constraint, but so is h. So the gradient of f now will equal a multiple lambda of the g, but since that's a different equation, we need a different multiple, which is they're using the Greek letter mu. So it's mu times. So all the constraint equations have to intersect with the function you're trying to optimize. They all intersect at the same point, tangential at the same point, meaning they would have the same normal curves, but the same direction of the normal curves, the gradient vectors, the normal vectors, gradient vectors, but then they're going to be different multiples. It doesn't mean they'll be the exact same vector. Sorry about that. I seem really tongue-tied here right now. So let's minimize this function, x squared plus y squared plus z squared. Now we're saying these are non-negative, so be careful here. Non-negative means 0 is possible. So we do not want to divide out possible zero solutions like I've been sort of taking for granted in some of these other ones, which was correct, of course. I wasn't wrong, but I was kind of conveniently dividing out variables because I knew we didn't need the zero solution. Okay. So now we have two constraints that must be satisfied, even though we're trying to minimize that function. But these two equations have to be satisfied where x plus 2z equals 6 and x plus y must equal 12. So now the Lagrange equations will expand a little bit. So now we're going to have fx will equal lambda gx plus mu hx. Fy will equal lambda gy plus mu hy. Fz equals lambda gz plus mu hz. So now you see we're introducing a new variable, which could potentially make the problem more challenging. So these partials for the left side, the function we're trying to optimize, would be 2x, 2y, 2z. And then now let's look at what the partials are going to be here. So that for the g, the derivative of x would be 1 respect to x. So we have lambda times 1. Over here we have x, so that derivative will be 1. And we have a lambda times mu. Let's go to the equation in terms of y. There's no y term here. So it's basically lambda times 0, which I then just canceled out. And here's a y here, though, so the derivative of y would be 1. And then for the third equation, we have a z here, so its derivative will be 2, so it'll be 2 lambda, but there's no z associated with the h, so it's mu times 0 here, so we can just kind of cancel those out. So here's, what I've been saying verbally a lot. I'm not sure if I ever wrote this out yet until now, but solve this by any algebraic method. So I generally just look at this and it's kind of a little different now. Obviously, it's with the single constraint, there might be some exception to this, but a lot of times, well, it did work for all the ones I did, but I don't want to say 100% of the time. But setting up the lambda equal tends to work well. But now we got a lambda and a mu, so it's a little trickier. Now here's what I did. Like I said, you might approach this a totally different way. And if you do it correctly, then it's just as good as my way. I took the middle equation and said that mu equals 2y. Middle of these three, which is number 2. That's why I numbered these. It's not a rule that you have to number them, but just so you can see what I was doing. Now I took number 3 and said that 2z equals 2 lambda, therefore lambda equals z. So now I substitute those values into the first equation. So lambda equals z and mu equals 2y. And then I'm going to combine them with those bottom two constraints. Now what I did here is I moved them all over and set it equal to 0. So this 2y that was right here, moves over, so it's 2x minus 2y, and then the z moves over, and it becomes negative z, so set that equal to 0. So I left that step out, but it was just substituting into here, and then moving them over. Now you got 3 variables, 3 unknowns. I did this algebraically, but you are completely free to use matrices if you feel comfortable with those in the calculator. You don't have to show all this work. But I just did do it manually for those of you that are going to possibly be doing it that way. Or if you're comfortable with, I didn't do it here, but if you're comfortable with row reduction properties, matrices, the Gauss process, Gauss-Jordan elimination, working those processes, if you're comfortable with that, you can do that too. But I just went with substitution, and I'm going to show you in the calculator. So this one, I just here's 3 equations, 3 variables. I took the middle one, solved for z, and I took the bottom one, solve for y. So z in terms of x, y in terms of x, and then go back to the very top one, everything will be in terms of x. So here's where the z, y in terms of x, z in terms of x, and I multiplied everything by 2 to get rid of this fraction, and I got all that. You can expand all that to get it to simplify. I got 9x minus 54 equals 0, so I got x equals 6. All right, so once we do that, y equals 12 minus 6 equals 6. And then z equals 3 minus 6 over 2, which equals 0. So you may remember from the beginning of the problem that it said it was non-negative. So 0 is a perfectly acceptable answer. This problem wasn't based on any kind of measurements or anything like that. The last problem was obviously finding dimensions of that box, so you could not have negative values. So we have x equals 6, y equals 6, z equals 0, so that would give us the order triple of 6, 6, 0. And then, did I find, jump ahead. Oh, okay, well I did it down here, but let's scroll back up. But yeah, you could get the minimum value, obviously, without using, the minimum value then would just be taking the original equation and putting 6, 6, 0 in there. So 6 squared is 36, plus 6 squared is 36, plus 0 squared. So 72 is the actual minimum value after you plug in the optimal values for x, y, and z. Yeah, so every matrix problem, you can't do matrices every time. If you had something with nonlinear components, that would not work. But these were all linear, no squares or cubes or anything. So I set this up. So now we had 5 equations with 5 variables. And so I set this up as x, y, z, lambda, mu. So you want to get them lined up in this order. So I moved the lambda and the mu. So here's what the system of equations would look like. So I had to get everything lined up with the number on the right side, and then get them lined up in order, because those coefficients are going to go into the matrix. Now I'm doing this kind of quick. You can obviously, if you need further research on using matrices to solve systems of equations, you can search for individual videos on that. But so here they are. I wrote them as the matrix. You would go in and you would edit the matrix. I just chose the first one, A. Obviously, if you had a matrix there that you were going to use for something else, you could go to a different one. But it's 5 by 6. 5 is the number of rows. 6 is the number of columns. So this is the process where you go matrix edit and you put in all the numbers. So after you do that, I always go second quit, and I go back to matrices, and I come down here to math, ref, and then I pick, I go matrix, I pick names, because I know I want to do it to matrix A, ref A, and then the right-hand column spits out the answers in the order that you had it across the top. So x equals 6, y equals 6, z equals 0. And we didn't need these, but I just want to point these out because we did get lambda and mu by doing it this way. So lambda was actually 0 and mu was 12. And there's the Lagrange multipliers and Maple. Maple does not distinguish between lambda and mu's. It just distinguishes them as a lambda 1 and a lambda 2. And then here's the 72, showing that that's the maximum value. So this time I did have the output equals detailed. All right, here's another one. Trying to maximize f of xyz equals xyz with constraints. It looks like a 9 there, but that's really letter G. There's h, so x plus y plus z must equal 32, and x minus y plus z will equal 0. This time we're saying they're all positive. And it kind of has to be for this one, because 0, you're probably not going to have a maximum value of 0. So 0 would wipe out everything here. So we set up the constraint equation. So the partial for here will be yz, xz, xy. And then the constraints for lambda, x, y, z, we have one of each, so it'd be 1, 1, and 1. So 1, 1, 1 for lambda. Mu, the partials will be 1, negative 1, 1. So we have 1, negative 1, 1. And then here are the two constraints. So kind of like here's where I just kind of tried to figure something out. I took 1 and 3. And I noticed, because I noticed there was a common lambda plus mu here. So I said that yz equals lambda plus mu, and xy equals lambda plus mu. So now if you set these whole things, so that they're both lambda plus mu, that means these two on the left side have to equal each other. So we have yz equals xy, and then z equals x. Like I said, the visualizing of how you should do this, can be a bit of a challenge. This one, because of these variables being multiplied together like this, it's nonlinear, so the matrix method would not work here. Well, I know that z equals x, so then what I did is take these bottom two equations and replace z with x, and then that reduces it to two variables and two equations, so then you can easily do elimination from there. So once I combine this, I have 2x plus y equals 32, 2x minus y equals 0. Add them together, you get 4x equals 32, which gives me x equals 8. And then once you know x equals 8, we know that z also equals 8, and therefore 2 times 8 plus y would equal 32. And then that gives you y equals 16. So the optimal value will be 8, 16, 8. Which ironically is the same answer to another problem we did, but obviously it wasn't the same problem. Of course, let's see. Then we could get whatever that maximum value is, so whatever 8 times 16 times 8 is. There I have it, 1024. Looks like I didn't put this one in maple, but I feel pretty good about the work here. Let's see. Oh, I jumped too far back, didn't I? All right. Oh, actually, I put this. Okay, yeah. When I got it 3 variables, 3 unknowns, I also showed that you could just do a matrix that way too if you wanted to for the 3 variables. But see, I couldn't do that until I got rid of all that, x times y stuff, or y times z. Now, this is an interesting example. We have this temperature function, 100 plus x squared plus y squared, represents the temperature in each point of a sphere where x squared plus y squared plus z squared equals 50. We want to find the maximum temperature on the curve formed by the intersection of the sphere and the plane x minus z equals 0. We have 2 constraints here. This first one, the equation, the sphere, and then we have this plane equation right here. So let's get our set of Lagrangian equations here. I wrote it out like this just to show you. But the partials then will be 2x for this one, 2y for the second one, and there's no z, so it'll be 0 here. Now the first constraint, oh, by the way, when you have 2 constraints, it does not really matter which one you call g or h. I just generally get in the habit of calling the first one I see g. 2x, 2y, 2z for the lambdas. And the bottom one, you have a 1 for the mu. There's no y there, so there's a 0. So that mu will cancel, and then minus z makes that a minus 1. And then here are the two constraints. So once again, I just kind of played around with this. I took the first, the second equation, number 2, and said 2y equals lambda times 2y. Now here's where you got to be careful. I don't want to divide variables here because there's no restriction on the values having to be positive or anything like that. So I don't want to divide both sides by, you've seen me do this earlier, but in this case I don't want to divide both sides by 2y, which would give me lambda equals 1, which is correct, but it also leaves out y equals 0. So for this equation there are two solutions. If lambda is 1, you have 2y equals 2y. But if y equals 0, then it zeroes out and you have 0 equals 0. So they both work. So now we have to consider then what solutions pair up with these two scenarios right here. So what I'm going to do is take the constraint equations, plural. I want to work with y equals 0. So I replace this 0 in the sphere equation. I get 2x squared equals 50. So once again, negatives are good here. They're okay. So I have plus and minus 5. Now that doesn't tell me, so if z equals x, that means though when x is negative 5 now, we know that from right here. Number 5 tells me that z equals x. So when x equals negative 5, z equals negative 5, and x is positive 5, z is 5, both working with y equals 0. So we yield these 2 points right here based on y equals 0. Now let's see what lambda equals 1 yields for us. So I took the number 1 equation and I have 2x equals 2x plus mu. That tells me mu is going to be 0 because I put 1 in for lambda here. Let's work with that. And now this tells me for number 3, I should zoom out of this for a second. So 3 will tell me that 0 equals 2z minus mu. So if mu is 0, that means z will be 0. So if x always equals z, so it will be 0. So now I have to solve the sphere equation with x being 0, z equals 0, and we'll solve for y. And that gives me y squared equals 50. Y equals plus and minus square root of 50. Yeah, if you look this up in a lot of textbooks or whatever, checking, they might have reduced that into 5 square root of 2. Not a big deal to me, but if you saw it somewhere else, it probably would have been simplified. So we essentially have 4 values here. So this is an example. We haven't done this yet, but I mentioned earlier on in the video that if you get 2 or more possible solutions, you just have to literally check them by plugging them in. So let's see if we're looking for a maximum or minimum here. Let's see. Maximum temperature. So I'm going to plug those 4 values into this function right here and see which one's the largest. And we actually have a tie. So obviously we include all ties. So the 0 root 50 0 or 0 negative root 50 0 yielded 150, which was greater than the 125. So we have a tie there basically. All right, I like that one. Now this next one, this one's kind of a little difficult. Probably not a question I would put on an exam per se, because the setup and everything is fine. It looks harmless enough. The algebra is get a little tricky. I've done this problem a couple of different ways. I think I actually found a much better way than I did before, but I could see how the solving of this would be extremely difficult. But we'll just kind of look at it. So if you can't follow what I did down here, that's all right. But anyway, we're trying to maximize this function x, y, z with x squared plus z squared equals 5, x minus 2y equals 0. So the partials over here are going to be y, z, x, y. For this one, I don't have a y, so I'll have a 2x, a 0. I just didn't show the lambda there. 0 lambda, and then 2z lambda. For the mu's, I'll have a 1 mu here, and a negative 2 mu there. And then the two constraint equations. So here's where it just gets kind of ugly. I just probably tried different things until it magically worked. But it looks like I took the second equation and plugged it into the first to get this, and then solved it for lambda, and and I multiplied everything here, by 2 over 2 just to get rid of that complex fraction, so that 2 wasn't there anymore. So I came up with this, and then I took equation 3 and substituted that mess into here for lambda. And yeah, believe it or not, this definitely was a better way than the way I had done it before, which I don't even remember. I just remember there was a lot more stuff than the way I did it before. So cross multiply, bring the 4x over, I get 4x squared y. Distribute through here, you get 4y z squared plus 2x z squared. So I brought over, I reduced it by 2. Then coming from the constraints, I know that y equals 1/2 x, and then z squared equals 5 minus x squared. So actually, I don't need to take the square root of this and solve, because I don't have to worry about that because we already have z squared right here, so we can just leave it as z squared. Oh, so jump too far ahead. So at this point, I took this left side. I put, everywhere I put a 1/2 x. Everywhere there's a y, there's 2 y's right here, so I got a 1/2 x. And then for z squared, I put 5 minus x squared in both places. Okay, looks like I reduced some 2's, canceled some 2's, and then divided by 2's. And I have to distribute on this side, obviously. So I have you distribute, you have a 5x. You're just left with x cubed on the left. 5x minus x cubed. 5x minus x cubed worked out to be 2 of the same thing. And then just combine. Once you get to this point, it's not too bad, but figuring out how to get to this was messy. So I just combined the terms. I moved them over. I got 3x cubed minus 10x equals 0. I don't want to divide by x because I want to keep, maybe I do. Let's see. Oh, all right. Well, excuse me. I could have divided by x there, since we only want positive answer. But anyway, whatever. I could have divided by x there, but that's all right. I just factored out the x. Was probably a good way to do things algebraically anyway. Then I just canceled it here, knowing I didn't need it. Either way is fine. The other one, you get x squared equals 10/3. Therefore, x equals the square root of 10/3. Y, by definition, is 1/2 x. Well, not by definition, by what we just solved for. So it's 1/2 of this. And then we know that x squared plus z squared equals 5. So I'll put this in there and get 10/3. 5 minus 10/3. 15/3 minus 10/3 is 5/3. So z equals the square root of 5/3. So here's that answer. I put this in the Lagrange multiplier. Of course, they rationalize their radicals, which I'm showing here, but my answer is equivalent to theirs. It just looks different, but it's the same as this answer right here. So Yeah, that one maybe was just on the edge of being exam worthy, maybe just a smidge too difficult because a little messy on the algebra. But anyway, well, that covers that's the end of this video for Lagrange multipliers.